Hello, everyone. My name is William Valentine. I am a senior computer science student at Rose-Hulman Institute of Technology, and this summer I've been working with Dr. Aaron Steinfeld on supporting blind individuals in navigating to intended robots. So, our motivation for this work is twofold. One, a lot of prior work has explored the issue of blind people getting onto buses easily. Um, there has not been a lot of work towards actually providing a concrete solution, but there has been a lot of work saying that there is a problem. Likewise, there's been work done to show that delivery services, especially those that deliver something to your house and then send you a photo of where they delivered it to, are really hard for people who are blind to use because they can't use the photo to actually find the goods. Um, and in the example of buses, buses generally are okay for blind individuals to use if they are consistently pulling up at the same bus stop. But even then, they present challenges. The idea that it might be pretty far from the curb, so you have to step out and you don't know if it's there. Where is the bus door? Do you happen to know if that's the right bus? What if multiple buses show up? And so there's a lot of issues that result in a number of blind people saying this is an issue and needs to be addressed. And so our thoughts, um, little work exists for this problem, and almost 300,000 people in Pennsylvania have a significant vision impairment. So, it's a substantial portion of the population. Some estimates go up to 6% of people in Pennsylvania. So that's pretty meaningful. Our research questions are: how can we develop a system to actually help solve this problem? How can the system be made as responsive and inexpensive as possible? And would the system actually be useful for blind individuals? So we'll be able to address the first two questions today, but the last question will have to be left to future work as the study for that with blind participants is in progress. So our problem constraints are the classic systems problems constraints. How can we make this system fast, effective, and cheap? The general idea here is we're going to use some cameras, so either a depth camera and a color camera or two color cameras to generate 3D boxes and then plan out paths for the blind individuals to be able to walk onto the bus or find the delivery robot, all while navigating around other people in that space. We then provide those paths to a mobile app and it speaks them out loud. So it translates them into sort of Google Maps-esque. So go forward, go left, go right, go this direction, this number of feet, so that it can be said easily out loud. And so the instructions are not just a path on the screen. So we have our two camera setups. We're using a fetch robot to represent a delivery robot with the color camera and the depth camera. And then our bus cameras, we mount them on a tripod, so about a 10-foot tall tripod. And then we have the cameras, two GoPros attached there. So the bus's cameras, our idea is that one of the cameras is facing outwards. So you can see in the side view of the cameras, one of the cameras is directly facing outwards and one of them is angled downwards so that we're able to use a little bit of reconstruction to reconstruct the scene and then figure out where people are standing. Because the concern is if you only use one camera looking outwards, one's not that accurate in localizing where people actually are. But importantly, a lot of people stand in lines while waiting for buses. And if you're standing in a line, then a camera that only sees the first person standing in line is not that helpful for figuring out more complicated paths to get onto the bus. So our proposed system for the buses is we take our two GoPros, we mount them on the tripod, and we attach them to a Jetson Xavier NX, which serves as our primary compute for both this and the delivery robot instances. So that does all of the computations for pathfinding and 3D boxes, and then generating the instructions. And then we have our mobile web app on the right-hand side. So this is a view of our cameras. We have them on our tripod. One of them is angled downwards, and the other one is angled forwards, so 0 degrees. So the first step we need to do is we've got our different camera views. We calculate our homography. What a homography is if you have multiple images looking different angles. This is not my photo. This is courtesy of a computer vision textbook out of MIT. So you might recognize this building. You see the multiple views that are fused together onto one ground plane so you can reconstruct what the whole environment is supposed to look like, even though you have just one view. So what we do is we take our two different views. You notice in this one, they're actually the same view, but that's just for demonstration purposes. We take our two different views and we're actually able to take the detection of people using a simple detector like YOLO, and we're able to create a 3D bounding box around the person actually very quickly and pretty accurately. So the second thing, which is sort of what I was alluding to, so we run YOLO 26 Pose. So we use the nano edition of that. So it runs on pretty lightweight hardware, such as our Jetson Xavier NX. On the networking, we do a lot of tricks with compressing images and compressing depths and getting everything to stream efficiently. And one of the things that we do is we have Ethernet wired from the Xavier to the Fetch, and we use USB cables from the GoPros to the Xavier, so we're not streaming anything. The last step is path planning. Path planning, we're just using a simple A-star algorithm where we're saying that all the pedestrians are obstacles, and so we inflate their size a little bit to make sure that paths never conflict with where pedestrians are standing. The proposed system for the delivery robot you'll see is very similar, except that one of the cameras is now a depth camera and the other one is a color camera, but everything else is pretty much the same. The depth is used to refine where the person's standing. Using points on the person's foot, we're able to take like the middle points in that box and say, okay, where are the depths here? Is this actually accurate to what our current estimates are? And then lean more towards where the depth is saying, at least at close range. The mobile web app just has very simple instructions there for our demonstration purposes only in the slides, because obviously if a person who is severely visually impaired is using an app that's relying on text, that doesn't really make sense. And so it's an audio-based system. It just for debugging purposes is showing text right now. Pedestrian identification. So how do you know if a person is blind and needs assistance? And so what happens, you have the mobile app and you press a button, I'm going to identify myself, and then you wave at the bus. And during that interval where it's waiting for someone to wave, then it's going to identify you as the person that needs support and is going to start planning a path for you versus some other random person. So this is sort of an example of what it looks like when the system's running. So we have our 3D boxes, and then we have our depth and our color cameras with YOLO running. And the bus example looks pretty similar, except that we've got two different camera views now. And we are computing our homography and applying it to be able to get our merged 3D and then see our path to the bus door. And so just a little bit of metrics, we can get within about 8.8 inches of where the person's standing. So that's where the person's foot is. So that's pretty good. I mean, for general purposes, considering our sort of inflation of people's standing, that's within, like the 90th percentile for this. So P90. And we think this works reasonably well as a proof of concept and would work reasonably well in practice. There's not a whole lot of situations where a person will be standing closer than 5 inches to you. And then just a quick example video. So I'm gonna mute the sound, but basically the app is talking to me, and then I'm going to start following its instructions. I'm going to turn, and then the robot is over here. Yeah. So let's revisit our problem constraints. Is it fast? Is it effective? And is it cheap? So the bus system runs 40 frames a second. So I would say that's pretty fast. Faster than we need it to be. You don't need to update somebody's position that many times to be able to give them a path. And the delivery robot side is a bit slower because we're doing a lot of stuff with depth, but still 17 frames per second. We can do 8.8 inches with the bus and 12 inches with the delivery robot, which feels within a reasonable threshold of error for determining where someone's standing at distances up to 40 or 50 feet. The overall cost we're estimating right now for the whole bus system is 1.3 grand, which we would say for given the average cost of a bus is pretty cheap to implement, and about $800 to implement on a delivery robot, assuming that you don't already have a color or depth camera. Future work is finish running our user study, refining the system, and then testing more challenge environments, which is always a good thing for systems, especially systems focused on accessibility. Getting those edge cases down is really important. I'd love to acknowledge Safety 21, CMU RIS, and a number of other awards, and a great number of faculty who've helped support me in this journey. If you're at all interested, you should definitely apply to CMU RIS, check out the eligibility, and see all the cool stuff that's happening next summer. Have a great day.